All right, let's dive straight into a classic concurrency puzzle, one that trips up even really experienced Java developers. We're going to unravel the whole mystery of the volatile keyword. And trust me, by the end of this, you'll get not just what it does, but why it's so incredibly important. So take a look at this code. On the surface, it seems totally straightforward. You've got a while loop that should run for about a second and then stop. But here's the weird part. A lot of the time, it just doesn't. It gets stuck in an infinite loop. What is going on here? Okay, here's the setup. We have one thread that's just looping, checking a running flag over and over. Then our main thread comes along and sets that same flag to false. Simple enough, right? The problem is the looping thread might just never see that change. So what's the fix? Well, the fix is surprisingly simple. It's not some complicated lock or a total redesign of the code. Nope, it's a single keyword. That's it. Let's see it in action. This right here, this is our problem line. Without any special instructions, the Java virtual machine is free to make an optimization. It lets the looping thread cache the running flag's value. To be fast, it just keeps reading its local copy and never bothers to check if the original has changed. And boom! By simply adding the word volatile, the problem is solved. It works exactly as you'd expect every single time. But, this isn't magic. It's all about how computer memory actually works. To really understand how that one little word fixed our bug, we have to talk about the official rulebook for threads in Java. It's called the Java Memory Model, or JMM for short. So why do we even need a JMM? Well, it's because modern hardware is all about speed. It has things like CPU caches, and it reorders instructions to be more efficient. That's great for a single thread, but it can create absolute chaos for multi-threaded code. The JMM gives us a set of consistent rules that all threads have to follow. Here's the key concept you need to get. Think of a central whiteboard. That's your main memory, shared by all threads. Now, each thread gets its own private notepad. That's its working memory, or cache. A thread copies variables from the whiteboard to its notepad to work on them. Our original problem? The looping thread just kept staring at its own notepad and never looked up to see that someone had updated the main whiteboard. And this is precisely what Volatile does. It's a command. It tells the threads, hey, for this variable, forget your private notepad. Every single time you read it or write to it, you have to go directly to the main whiteboard. This guarantees visibility. It ensures everyone is looking at the same up-to-date information. Now, it's super tempting to think of Volatile as this magic wand you can wave to fix any concurrency problem, but that is a really dangerous trap. It solves one very specific problem, and that's it. So let's bust a few myths and talk about what it can't do. Okay, if you're ever in a technical interview, this is the line to remember. Say it with me. Volatile fixes visibility, not race conditions. It guarantees you will see the latest value, but it does absolutely nothing to make sure a sequence of operations is safe from interruption. For example, take a simple operation like count++. It looks like one thing, right? One step. But it's a lie. Under the hood, it's actually 3 separate steps. Read the value, add 1 to it, and then write the new value back. Even if count is volatile, another thread can sneak in between those steps and you can end up losing updates. This is not an atomic operation. So, let's make this crystal clear. With Volatile, what do you get? You get 100% visibility, guaranteed. What don't you get? You get 0% atomicity for those compound read, modify, write operations. And this table just lays it all out. It really shows why Volatile can't replace a synchronized block. See, synchronized is the whole shebang. It gives you visibility, sure, but it also gives you atomicity for entire blocks of code and mutual exclusion, meaning only one thread can be in that block at a time. Volatile is a much lighter, more specialized tool. All right, so we've covered the what and the whatnot. Now let's get to the core principle that really governs all of this. It's a concept from the Java memory model called the happens before relationship. It's the formal framework for all this stuff. Think of happens before as a contract, a formal promise from the JMM. If the rules say that action A happens before action B, it's a guarantee that everything action A did, especially its memory writes, will be perfectly visible to the thread that's about to perform action B. No guesswork involved. Now, the JMM has a bunch of these rules for things like locks and starting threads, but check this out. The one that matters to us right now is the volatile variable rule. It states that a write to a volatile variable happens before every subsequent read of that same variable. That's it. That's the formal guarantee, the why behind our fix. It's the rule that makes the magic work. Okay, we've gone through the problem, the fix, the deep theory, and the limitations. Let's put this all together into a practical toolkit that you can actually use in your code and, of course, ace that next interview question. So here's the bottom line. Use Volatile for simple status flags. Think things like running is shut down or is ready. It's perfect when one thread writes to the flag and other threads just read it to know what to do. But the second a variable's new value depends on its old value, like with a counter, Volatile is the wrong tool for the job. You need something stronger. And here it is, your killer interview line. If you want to show that you don't just know the what, but the why, this statement is gold. It connects the Java memory model, Volatile, the happens before relationship, and the core philosophy of writing correct, reliable, concurrent code. It shows you get the big picture. So, hopefully this gives you the tools to not only fix bugs, but to start seeing your code through a new lens, the lens of the Java memory model. Concurrency isn't just random bugs, it's a system with rules. And now that you know the rules, the real question is, what puzzles are waiting to be found in your own code?